we used this methodology of building MOFs to make a material that had an extraordinary surface area. The big news was that you could make a material that is larger on the inside than the outside, and that a gram of that material could cover an entire football field if you're talking about the space that it encompasses. So this was really a breakthrough that people stood up and paid attention to this chemistry.
Metal organic frameworks, or MOFs, are seemingly enigmatic chemical structures with groundbreaking applications across medicine, climate science, and more. This year, 3 scientists were awarded the Nobel Prize in Chemistry for their work in MOFs, including Omar Yaghi. Dr. Yaghi is also the recipient of the 2025 MRS von Hippel Award and is here now in the studio with us to tell us more about his history-making discoveries. Such an honor to have you with us today.
Thank you very much.
This is really exciting. I want to talk about your work in just a second, but I really want to get started focusing on your personal journey, because you came to America from Jordan as a teenager, but it was at the insistence of your father. Why were you initially reluctant?
Well, I mean, I was only 15 years old and I didn't want to leave home. I wanted to stay there, finish my high school and college and try to find a job there. But I think my father had different plans and he saw opportunity elsewhere, and I guess he was right.
Why was he so insistent on you coming to America for your education?
Well, you know, I grew up in a refugee family in a humble home, no running water or electricity. So we were, our focus was entirely on education. My parents spent their whole life spending every hour working for the kids, making sure the kids are going to the best schools and so on, and they've never had a holiday. So you can imagine that when there's an opportunity, they definitely jumped on the opportunity for me to go to another country where perhaps I can improve myself more.
Incredible. Yeah. So you arrived in the U.S. and you began your studies at a community college in New
Yes,
York
yes.
Before transferring to the University of Albany. How did those early experiences shape your overall career trajectory, do you think?
Well, when I got to the U.S., I called back home and I said, what do I do now? And they said, well, take the marks that you had from 9th grade and go to the nearest college. The nearest college was Hudson Valley Community College. Well, I took classes there and I did well. And they said, sure, we'll admit you. And so I was admitted at the age of 15, 16 into college, and then I transferred to Albany. Now it's called the University at Albany. Mm-hmm. I took organic chemistry class, and during this class you have to do a laboratory where you crystallize organic compounds. And so when I saw the crystals of these organic compounds falling out of solution almost like snowflakes, I thought, wow, I was really captivated. I turned to a colleague of mine in the lab and I said, look at this, isn't this fantastic? Well, I was in love with these crystals. But you know, my interest in chemistry really started back in Jordan, when in my school, where I went to the library and I found molecular drawings. I didn't know they were molecular drawings. I was only 10 years old. Mm-hmm. But when I discovered that they were molecules, I was truly captivated, and that love for molecules stayed with me.
So then when did your fascination with MOFs begin?
Well, when I was a graduate student, I was getting more and more interested in using molecular building blocks to stitch those molecules together and make new forms of compounds. It's almost like Lego chemistry, taking Lego pieces, putting them together to make different forms, and that's exactly what we were able to accomplish.
And so speaking of which, how is it possible for these materials to be bigger on the inside? That's hard to comprehend.
Yes, so you could take organic units and inorganic units and stitch them together to make porous structures, and these porous structures have so much space inside them that you could say they're larger on the inside than outside. 1 gram of a MOF is equivalent to the space that you would have in an entire football field. It encompasses that much space. One of the best ways, let's say, that I could explain it is that if you take this room and you have some bees in the room, mm-hmm. and you introduce a small honeycomb, mm-hmm. the bees will come and assemble themselves on this honeycomb. So when molecules are far away from each other, like the bees in a room, and you introduce a MOF, and the MOF is programmed to attract those molecules, now you could stack molecules on the internal surfaces of the MOF that you can have so much in a small volume that you couldn't have without the MOF. So the way the MOF basically works is that if you zoom in on a granule of MOF, okay, they look like baby powder or granulated sugar.
Okay.
So if you zoom in on the atomic level and your eye can see on the atomic level, you'll see a granule basically that's riddled with holes, billions and billions of holes.
Okay.
And each hole exposes an internal surface into which you could stuff molecules, trap molecules, and compress them without having to use high pressure or low temperature.
The honeycomb analogy is very helpful. Let's talk about a really great achievement that you had. You had a breakthrough in being the first to synthesize MOF5. Can you explain what made this discovery so impactful and then how it stood out from other MOFs at the time?
Right. So in the mid-1990s, we were the first to discover a way of crystallizing metal ions with organic linkers that are charged. And the reason I emphasize charged as opposed to the neutral organic linkers that were used prior to our work is that they create much stronger bonds. And this becomes really important later when we talk about carbon capture and having a material that stays in a power plant for years, capturing carbon dioxide rather than days. The bonding becomes really important. The bonding between the building units has to be so strong that they're not going to break apart over time. So in 1995, we showed how you can make them in ordered form. In 1998, we showed that they can remain open in the absence of any stuffing, any molecules that would stuff the pores and keep them open. When you take those molecules out, the structure remained open. In other words, they had permanent porosity, and we showed that in 1998. Nobody paid any attention in these two studies. In the 1995 study, 1998 study, we knew that they were important milestones. But in 1998, we used this methodology of building MOFs to make a material that had an extraordinary surface area. It had a surface area that was 6 times higher than the previous state-of-the-art material, like the traditional ones, like zeolites, or let's call them inorganic porous materials. Well, this was a big news. Mm-hmm. The big news was that you could make a material that is larger on the inside than the outside, and that a gram of that material could cover an entire football field if you're talking about the space that it encompasses. So this was a big deal. And also it was a big deal that you took organic units and inorganic units, many are possible, to put them together to make many or countless number of MOFs. So this was really a breakthrough that people stood up and paid attention to this chemistry.
But you said people were, I guess they kind of ignored it at the moment. You realized, though, in that moment, the significance of this breakthrough.
Well, I think when we reported the extremely high surface area, I think people began to take a closer look.
Okay.
Now there were a lot of doubters, like any new discovery.
Right.
There'll be a lot of
skeptics.
There are skeptics and a lot of doubters, but that's okay. And over the years, we've discovered many things, like that since 1999, and we've always had people who criticized and who were detracting from the actual intrinsic advance that we have made. And I developed what I call the 95% rule. When 95% of people are not endorsing or not seeing the impact of the work, 5% will always see that and support you. And I think that that's important as researchers, to know that in our journey, which is full of failures or what we call increments to success, that you need that 5% to make you, eager to move forward with all the critique. But I also wanted to say that critique is very important.
Right.
You take a critique that is legitimate to strengthen your work, but stuff that you think is not legitimate, you can throw away.
Right. I want to talk a little bit about maybe some possible real-world applications. And in particular, you've pioneered applications in water harvesting. Given the boom of AI and the subsequent need for these huge data centers and the increased water consumption, do you feel that there is pressure to scale your technology to try to meet the growing demands of these data centers?
Absolutely. I'm glad you mentioned that. That's a great application. And it's one of the ones that we're focusing on in this company that I'm involved in Southern California. Atoco is already, has been testing prototypes that deliver about 100 liters per day. And these are tested under different conditions of desert and arid region, as well as the humidity, and they operate very, very well. And their next step is in 2026 to unveil systems that are delivering up to 4,000 liters per day. These are electrified systems that run with energy efficiency, as well as they produce extremely clean water. And you're absolutely right. These data centers generate a lot of heat. You need water to cool down the different things in these data centers. And you can also use this waste heat that they generate as a way to do the water harvesting. So it's a great way of not just cooling them down, but also using any waste heat that might be out there to help with the water harvesting.
Incredible. Really a cycle there.
Yes.
Incredible. Any other applications of MOFs that you're really excited about at the moment?
Sure. I mean, MOFs are already capturing CO2 from cement plants in Canada.
Okay.
So one of my colleagues invented a MOF in the same way that I have been describing the synthesis of MOFs, and this MOF is being scaled up to hundreds of tons by BASF for plants, cement plants. Cement plants produce almost 1/3 of the total industrial CO2 emission. So this is a very, very much a worthy goal, is to trap CO2 from cement plants before it reaches the atmosphere.
So you've been awarded the Nobel Prize for your research. Huge congratulations. I mean, what an incredible honor.
Thank you.
What's next for you?
Well, what's next is that this is only the tip of the iceberg. I mean, there's just so much more to do. There are covalent organic frameworks. We've already shown that they could be used to take CO2 out of the air. There's a lot of CO2 in the air, almost 1,100 gigatons of CO2 that is in the air, that is extra CO2 that we need to take out of the air. And at the end of 2024, we reported an amazing COF 999, and it's capable of plucking CO2 out of the air. We can take Berkeley air and pass it through the COF 999 and show, in fact, that you can trap CO2 from air, and you can do this repeatedly for hundreds of cycles.
Wow.
Without the material degrading, which was a challenge for many CO2 capture materials. And it's a solid. So it's not a toxic solid. You know, the traditional processes for CO2 capture from air involve liquid amines, and the liquid amines are toxic. They degrade, and they also consume a lot of energy in their process of taking up CO2 and releasing it. And so the COF overcomes all of these challenges, and it's pointing us to a new direction in terms of applications of COFs. The other application for COFs, or in terms of the future, is molecular weaving. We can actually make molecularly woven materials that's just like the cloth that we wear. And these have incredible mechanical properties. They enhance, if you take 1% by weight and add it into a material, it makes the material harder and more resilient. Most of the time when you put additives into materials, they become harder, but then they become more brittle. With these woven materials, they become harder, but also they become tougher, less brittle. And so this can be transformative for many applications, automobile parts or aerospace applications.
Defense.
Everything. Yes, exactly.
We started off talking about your personal journey and you coming as a teenager from Jordan. So I want to wrap up today with kind of going back to your personal path. And you talked about starting off, living in Jordan in very rustic conditions. Your thoughts now with the incredible life that you've had and the recognition that you're receiving now for your work, being a Nobel Prize winner, your thoughts on really how far you've come?
Well, I think immediately in a recognition like this, which is the ultimate recognition for a scientist, immediately you think of the people that helped you along the way. And many of them, fortunately, are living. My parents are not living anymore. I wish they were, because they would have treasured this time, so that's important. What's also important is that one person cannot create a whole field. The amazing thing about the MOF field is that it was able to bring in all these brilliant people who in their own right became stars and contributed meaningfully to this field, and they became pillars of the field. So I think that this is also a tribute to them, to my former students who worked so hard and failed and failed and failed so that they can succeed and so that they can push the science forward. This is a time when we celebrate. We celebrate recognition of our field, celebrate the people who've sacrificed for the field. But like I said, this is only the beginning.
That's wonderful. Well, huge congratulations to you. And
thank you
so much for sharing your expertise and your time with us today.
It's my pleasure. Thank you.